Good afternoon, students. Today we will discuss how can we derive transfer function from state model. Consider the standard state model for linear time invariant system is given by dx by dt is equal to a x of t plus b u of t. This is state equation. A is system matrix, B is matrix, X is state variable vector, and U is input vector. Y is equal to C x of t plus d u of t. Y is output, and this equation is known as output equation. Taking Laplace transform of both sides of first equation, we get s x of s minus x of 0 is equal to a x of s plus b u of s. Similarly, taking Laplace transform of this second equation, we get y of s is equal to c x of s plus b u of s. Since system is time invariant means it means that these all the four matrices are constant. And in this case, we define that initial condition, or we assume that initial conditions are 0. Hello. Assuming that initial conditions are 0, x of 0 is 0. So this equation can be written as s x of s is equal to a x of s plus b u of s. Or we can write this equation in this form as s x of s minus a x of s is equal to b u of s. Here s is an operator and a is, in this case, a is matrix. And order of this matrix is n cross n. This is system matrix. So to match the order of these two terms, because this is an operator, so to match the order of this matrix, here we take an identity matrix I. Yeah. And order of this identity matrix is same as the order of A matrix, means order of both I and A is same, n cross n. So we can write this equation here we write that Si minus A is equal to x of s, s minus A, Si minus A multiplied by x of s is equal to b us. Then multiplying both sides by s minus A, Si minus A inverse, we get the value of x of s, and value of x of s is inverse of Si minus A multiplied by B multiplied by us from this equation. And if we substitute the value of x of s in equation this equation, we can say that if we substitute the value of x of s in this equation, we get the value of ys, and ys is equal to c inverse of si minus a multiplied by b multiplied by us plus d us. US is input vector, Y is output vector. So here we get YS divided by input, which is transfer function. So from state model we get the value of transfer function. Transfer function TS is given by YS divided by US is equal to C inverse of S I minus A multiplied by B plus D. Clear? Value of this inverse of Si minus A is written as adjoint of matrix Si minus A divided by determinant of Si minus A. So from a state model we can easily calculate the transfer function of the system. Remember that state model of a system is not unique, but transfer function obtained from any state model is unique. It is independent of the method used to express the system in state model form. This is a equation for transfer characteristic, and we know that if we equate the denominator of transfer function is equal to 0, then we get the characteristic equation. So if in this case, if we equate determinant Si minus A is equal to 0, this is the characteristic equation. And we know that stability of a system depends upon the roots of characteristic. In matrix algebra, the roots of characteristic are called eigenvalues of matrix A, and these are generally denoted by lambda. Means this is the characteristic equation, and if we calculate the roots of this characteristic equation, these are known as eigenvalues and eigenvalues of matrix A. Clear? Consider a system having a state model. Consider a system having a state model given by this. This is A, B, and C. Here D is 0. Then obtain its transfer function. Transfer function is given by C matrix multiplied by Si minus A inverse multiplied by B. First you calculate the adjoint inverse of Si minus A. It is given by adjoint of matrix Si minus A divided by determinant of Si minus A. Calculate S multiply distance. This is my identity matrix 1 0 0 1 minus A. A is minus 2, minus 3, 4 and 2. So this is Si minus A. This can be written as this. So S plus 2, S plus 2, then if we 0 plus 3 here, S plus 2 and plus 3, then 0 minus 4 minus 4 and S minus 2 S minus. Then adjoint of this matrix is calculated simply by calculating the cofactor C11, C12, C21 and this, and transpose of this matrix. Then cofactor of this first S minus 2, S minus 2, S C12, C12 means first row, second column minus 4, and since 1 and 2 it means that it is 4. Then C21, C21 means second row, first column we get minus 3, 2 plus 1 is 3, so minus 3, and last one is C22 means second row, second column S plus 2, and transpose of this matrix is In if we take transpose of this matrix, it means that this row will become column in this case. So S minus 2, 4 minus C, S plus 2. This is the adjoint matrix of Si minus A. Then calculate the determinant of S minus A. Determinant of S minus A, S plus 2 multiplied by S minus 2 plus 12. So this is the determinant value. So inverse of Si minus A is given by adjoint of Si minus A divided by determinant of Si minus A. This is the inverse value of Si minus A. Then transfer function given by C multiplied by inverse Si minus A multiplied by B. Value of C in this case is this and B is this. So if we substitute the value of C, adjoint inverse of Si minus A multiplied by B divided by S square by 8, and when we simplify this matrix we get the transfer function of given. Then multiple input and multiple output system. For multiple input and multiple output system, a single transfer function does not exist. There exists a mathematical relationship between each output and all inputs. Between each output. If there are two outputs, then there are relationship between both outputs to all the inputs. Hence, for such system, there exists a transfer matrix rather than transfer function, but the method of obtaining transfer function remains the same as in the previous case. Determine the transfer matrix for multiple input and multiple output system given by this equation. There are two inputs, two outputs, and this is the state model. The given state model, from the given state model, value of A is this, B is this, C is this, and value of D matrix is 0. Then we can easily calculate the transfer function. We can easily calculate the transfer function. Transfer function is given by C, inverse of Si minus A multiplied by B plus D. Value of D is 0 and Si minus A is easily calculated, which is equal to S minus 3 to S plus 5. Then calculate the adjoint of this matrix. C11 is S plus 5, C12 this 3, and since 1 and 2, so this is plus sign, so this is 1 minute. C12 is first row and second matrix means 2, and since it is 1 and 2, j minus j raised to power this is minus raised to power 1 plus 2 is 3, so minus 2, and C21 second row first column, second row first column, so it is 3, and second row and second column is S. Take the transpose of this matrix. For taking transpose of this matrix, this row will become column S plus 5 minus 2. This row becomes column 3 and S. And take the determinant of Si minus A. Si minus determinant of Si minus A is S multiplied by S plus 5 plus minus 6. Minus 6. So we get this is the determinant value of Si minus A. So inverse of Si minus A is adjoint matrix Si minus A divided by determinant Si minus A. Adjoint of Si minus A is given as this will be calculated. Adjoint of matrix is given by this matrix and determinant is given by this. So substituting the values of adjoint of Si minus A and determinant of Si minus A is given by this. So transfer function is given by C inverse of Si minus A multiplied by B, and we get this equation. By solving these matrix, we get this is the transfer function, and we know that transfer function is output. Here output is Ys is equal to transfer function or transfer matrix multiplied by input matrix or input vector. So we can say that there are two outputs, two inputs and two states. So we can write this as y1s by y2s transfer function multiplied by u1s and u2s. And this relationship indicates that each output depends upon both input, means y1 depends upon u1 and u2, y2 also depends upon u1 and u2, means each output depends upon both inputs. And obtain the transfer function if state model is given by this equation. State model is given by state equation and output equation. In this case, value of D is 0, A, B and C. This is the A matrix, B matrix and C matrix. And we know that transfer function is given by C multiplied by inverse Si minus A multiplied by B plus D. Value of D is 0. Si minus A, Si minus A, and if you solve S plus 0 S, if we solve this, we get the value of Si minus A. Then inverse of Si minus A, first calculate adjoint of Si minus A. Adjoint of Si minus A is given by C11, C12, C21 and C22. Transpose of this matrix, cofactors matrix. So first is C11 means this and this S plus 3. C12 first row second column means minus 2. C21 second row first column 1 and second row second column means F. Then take the transpose of this matrix and Transpose of this matrix is given by S plus 3, 1 minus 2S, and determinant is simply S multiplied by S plus 3 plus 2. So S square plus 3S plus 2 multiplied by this. So we get the inverse of Si minus A is given by this, and if we multiply this matrix with C and B, we get the transfer function. This is the value of C and the value of B. So if you simplify this, we get the transfer function. Consider the single input, single output system whose state variable description is given by this. This is the state model, means state equation, and this is output equation. Then determine the transfer function. Formula used: Ts is given by Ts is equal to C inverse Si minus A multiplied by B plus D. Value of A, B, and C is given, and we calculate the value of Si minus A. Then calculate inverse of Si minus A. Inverse of Si minus A is given by adjoint of Si minus A divided by determinant of Si minus A. Then calculate the adjoint of this matrix, which is this, and determinant of this matrix, it is given by this equation. Then multiply in this by C and B, we get the transfer. Suppose the solution of homogeneous state equation, suppose dx by dt is given by ax of t plus b ut. This is the state equation, and for homogeneous system, ut is 0, input vector is 0, then dx by dt is given by ax of t. If we take Laplace transform of this, we get s x of s plus a x of s plus x of 0. This is the initial condition. So we can write that x of s is si minus a is equal to x of 0. Then x of s is equal to si minus a inverse multiplied by x of 0. This inverse matrix si minus a, here it is psi of x, and this psi of x is known as resolvent matrix, and if we take the inverse Laplace transform of this, we get the state transition matrix. Suppose that this is the state equation, and we have to obtain from this state equation state transition matrix. A is this, B is this is the state vectors, these are the state vectors, and this is input vector. Psi of t is inverse of Si minus A inverse. So first calculate the value of Si minus A. Si minus A, this is Si minus A, and if you solve this, you get the value of which is Si minus A. Then inverse of Si minus A is adjoint of Si minus A divided by determinant of Si minus A. Then this is the adjoint of it. Si minus A. This is a determinant of Si minus A. And if we take transpose of this matrix, we get S plus 3, 1 minus 2 S. And if we solve, we get the value of inverse of Si minus A. In previous, here Si minus A inverse is written as resolvent matrix. So Si minus A inverse is written as psi of S, which is written like this. And if we take inverse Laplace transform of psi of S, if we take inverse Laplace transform of psi of S, this term reduces to 2 exponential minus t minus exponential 2t. This term reduces to exponential minus t minus exponential minus 2t. Similarly, minus 2 exponential minus t plus 2 exponential minus 2t and minus exponential minus t and plus 2 exponential minus 2t. And this is the state transition method. Find the state transition matrix for A is equal to 0, minus 1, plus 2 and minus 3. Use Laplace transform method. Si minus A. S is this, Si minus A, and we get the value of matrix Si minus A, S plus 1 minus 2, S plus 3. Adjoint of this matrix is C11, C12, C21, C21 and C22. Transpose of this matrix S plus 3 2 means this row will become column and this row will become column. So transpose of this this is the adjoint of Si minus A is given by this matrix. And then take the determinant. Determinant is simply S multiplied by S plus 3 minus plus 2, which is equal to this. So we calculate the inverse of Si minus A, which is given by adjoint of Si minus A divided by determinant of Si minus A, and this is resolvent matrix, which is given by this. And if we take inverse Laplace transform of this, we get the state transition matrix. If we take inverse Laplace transform, we get 2 exponential minus t minus exponential minus 2t here minus exponential minus t plus exponential minus 2t. In this case, 2 exponential minus t minus 2 exponential minus 2t. Similarly for this. And we get the state transition method. Now time is over. Thank you.